All right, welcome back. Today is September the 21st, and there goes our summer. So thanks, Kavi. Kavi already stole springtime and summertime from us. So great. Now we're going to have to start another season uh, with it. All right. So I'm going to start this class now. We're going to begin chapter 5. Now, chapter 5, it's a bunch of concepts. I don't know if you noticed, the practice homework is nothing but concepts. Now, as we move into chapter 6, then that's a different beast, kind of. So, chapters 2, 6, and 9 for this semester will define your grade. So it's your ability to, focus and concentrating on dominating these 3 chapters, what's going to help you out in the long run. Chapter 2 was acid-base. It was a kind of hard subject to master. Chapter 6 is something new. It's for the first time that you're going to be seeing organic chemistry reactions. So you're seeing general chemistry reactions where you have like solutions and ions exchanging, that kind of thing. But for organic chemistry, the idea of organic chemistry is bond breaking, bond making. So based on that, it's a totally new ball game. And so chapter 6 will be challenging for you guys. Chapter 9 it's also going to be really rough because it deals with 4 different types of reactions. Elimination reactions 1, elimination reaction 2, substitution reactions 1, nucleophilic substitution reaction 1, and nucleophilic substitution reactions 2. So SN1, SN2, E1, E2, which is hard to master, honestly. It's kind of difficult, but there you go. Once we move into next semester, we have a variety of things. We have spectroscopy to start. Then after that, we have a whole bunch of synthesis and nomenclature. And in the end, we'll have carbohydrates. You take a little breather, so we start getting into the biological kind of molecules. So that's how that goes. But chapter 5, why is chapter 5 important? So chapter 5 is very important because you need to calculate degrees of unsaturations. Degrees of unsaturations are also known as index of hydrogen deficiency for other books, IHD. So most people know this as DUs. So what is a DU? What is a degree of unsaturation? Well, if you have a ring, a double bond, you have a degree of unsaturation. A triple bond will have 2 degrees of unsaturation. Basically, a degree of unsaturation means you have lost 2 hydrogens. All right? So we're going to start this chapter of alkenes with determining DU at first glance. So here you have the structure of butanol or butan-1-ol, or 1-butanol, depending how people calls this. But we've learned it as butan-1-ol. As you can see, it's linear. All the bonds here for butan-1-ol are single. The oxygen will have 2 lone pairs, and so the degrees of saturation will be 0. So you hear about saturated fats by any chance? Saturated means they have been filled with hydrogens. The double bonds have been reduced with hydrogens. All right. If you look at the next molecule, it's a diene. So this molecule has 2 degrees of unsaturation because it has 2 double bonds. The next one is the second one is called 1,3-butadiene, right? The third one is cyclohexene. It's a cyclohexene with a double bond, so makes it a hexene. It's a ring, so you don't need to, and it's only the only functionality is the double bond, so you don't need to put the 1, so it's cyclohexene, it's fine. That one has 2 degrees of unsaturation. It has the ring, that's 1, and the double bond, that's 2. The fourth molecule that we have here is an amide. Notice that we have a triple bond and a double bond. So the triple bond contributes with 2 degrees of saturation, and the carbonyl with another one. So in total, we have 3 degrees of saturation. The last one on the right side is your good old benzene ring. The benzene ring has 4 degrees of saturation. 1 is the ring itself, and then 3 more are the double bonds. So that makes a total of 4 degrees of saturation. So that's what we have here. All right. So the next slide tells you how to calculate the DU. So we're going to memorize this formula. So do you remember what other formula had this 2 times n plus 2? Anybody?
Formula for alkane.
The formula for the alkanes, exactly. So the 2 represents the 2 terminal hydrogens in the carbon chain of the alkanes, and so the DUs use that. So it's 2 times n, where n is the number of carbons in the molecule, plus 2 minus x. We're going to define x in a minute. So basically the DU means that the maximum number of H's is represented by 2n plus 2. And then the actual number of hydrogens is x, defined as x. So you're going to subtract the actual number of hydrogens from the maximum number of hydrogens possible. And then you're going to divide that by 2. All right, x is the number of actual hydrogens. All right, so check this out. We're going to see that when we have oxygen in the molecule, it doesn't affect the DU at all. So it doesn't have any effect on the DU calculation. So oxygen equals to none. Halogens, they count as an actual hydrogen. So a halogen and a hydrogen, they need to be added. All right, in the DU. In the number, for the number of x. So x is defined then as the number of hydrogens plus halogens. Anything that starts with an H, remember, that's going to be your x. All right? Then nitrogen. Nitrogen does have an effect on the maximum. So the maximum number of H's, you had to add 1 more number. So you increase it by 1 for every nitrogen that you have. So if you have 1 nitrogen, then your formula becomes 2 times n plus 3 minus x divided by 2. All right? If you have another nitrogen, then it will become 2 times n plus 4. So you keep adding 1 extra atom, because nitrogen can form 3 bonds, right? And that's why the 3 stands for n2n plus 3 means you need to have 3 bonds around that nitrogen. All right, so I have here some selected examples. Notice that I have a molecular formula that says C7H14Br2. All right, so my DUs will be 2 times the number of carbons at 7 plus 2 minus 16. Notice that I have 14 hydrogens and 2 halogens, 2 bromines. So that's a total of 16. So it's 2 times 7 is 14 plus 2, 16. 16 minus 16 is equal to 0. 0 divided by 2 is 0. So if I ask you to write an example of a molecule with those DUs and that molecular formula, I chose this. This would be 1, 2, 3, 4, 5, 6, 7. This would be 1,2-dibromo heptane. right? So that would be my example, the example that I picked. You can choose any other combinations. The example on the right side, C8H9NO. You can calculate the DUs as follows. So it's 2 times the number of carbons, 8. 2 times 8, 16. Notice that I have a nitrogen, so I'm going to put a 3 there right away. 2 times 8, 16 plus 3, minus the number of X's. In this case, we only have hydrogen, so it will be minus 9. So 2 times 8 is 16. 16 plus 3 is 19. 19 minus 9 is 10. 10 divided by 2 is 5. All right, so I have 5 degrees of unsaturation. One structure that you could use to knock off a bunch of these DUs would be something that looks like a benzene ring, right? The benzene ring has 4 degrees of saturation right away. So you have the ring plus the 3 double bonds. That's a total of 4. In this case, I had an amine. I had a nitrogen, so I put that inside of the ring because this is what I just came up with. This molecule here, just this ring, 6-member ring, 5 carbons and 1 nitrogen, is called the pyridine ring. So this, for the future, you're going to be talking about, when we talk about this is known as pyridine. All right? And so we have a carbonyl group that adds the other degree of unsaturation to make it 5. And then I had to have 8 carbons. So I have 5 carbons in the ring, 3 on the chain, that's 8. I have 1, 2, 3 hydrogens on the ring, and let me see. No, I have 1, 2, 3, 4 hydrogens on the ring and 5 on the chain. That's a total of 9 hydrogens, 1 nitrogen, 1 oxygen. I'm good. And so that is a molecule on the right that has 5 degrees of unsaturation. All right? All right, cool. I'm not going to go through this example. We have plenty of examples that we're going to do on the practice homework. But what I wanted to give you is an overview of what we're going to be covering in Chapter 5. All right, you know how to name alkenes already. We have done alkenes more difficult than this. We have done them with E and Z, R and S, you name it, and with functionality around them. So these examples are actually pretty light compared to what you know already. So I'm not going to spend any time. We'll spend a lot of time on E and Z, and that's when this chapter starts it. That's what I like to do with my chapter. Sometimes I like to sprinkle it at the beginning, and by the time we get there, we already know. We already know it. So it's kind of like review now at this point. So I'm not going to go through this unless there's someone who wants to clarify E and Z before we move on. There's always that possibility. And I'm fine with, explaining a little bit. But we spent a whole week on this. So I feel confident that you guys know this stuff. We also talked about here the neither, this one, because this one has 2 of the same group attached to the double bond, so it is neither Z or E. Here examples are of Z and E's, and that's based on the priorities and the atomic number of the atoms that are connected directly to the double bond. And you work from your double bond out. You never go back to the double bond. All right? The only time you go back to the previous atom is when you have a double bond or a triple bond and you're dealing with a tiebreaker. Remember that? So if you have a triple bond competing with a T-butyl group, the triple bond wins because it has it'll have 3 carbon connections plus the hydrogens. That's 4 connections plus the end of the triple bond of the T-butyl groups will be carbons connected to 3 hydrogens. So we learned that. All right. Let's see. Now, this is what I want to spend some time. Before we get into the thick of things here, I want to go through these 4 reaction coordinates and explain why this is important. All right? Many of the students that take OCHEM and then they start going by the motions, they just think of OCHEM as maybe a recipe. Oh, I'm going to follow this recipe. I'm going to do this in the lab. But I want you to visualize what's happening, especially when you do a reaction. Think of what is your intermediate at a certain point, what are your products at a certain point, when you're going to work up the reaction, where do they go? Like when we did the benzoic acid, we put the main core of the atoms in 2 different layers at different points by changing the pH. So, the reaction coordinate diagrams tell us how the reaction is behaving. The reaction doesn't have a brain, but it behaves in a way. And so we have to figure out how that reaction behaves so that we can control it, all right? When you make a drug, and this is one of the coolest things that scientists figure out, we figure out that when we control the temperature, we can control the addition of the reagents into the reactions. We also can control the kinetic versus the thermodynamic product, and that's because of the heat, because of the ability for the reaction to either absorb or release heat. So check this out. In the coordinate reaction coordinate diagram A here, we take a look at this diagram. Actually, I went on really good details on my videos recordings, but I want to still give you a little summary of it. So notice that we're dealing with something called delta G, which is the free give energy or free energy of every reaction that happens. So notice that a reaction starts on the left side with the R where the reagents are, and then goes over a hump, and that is called your activation energy or transition state. And then after going over the hump, it forms product, or P, right here in green. So notice that this reaction has a delta G that is negative. I'm sure you are familiar with these terms because all of you took GChem 2. And so this is the part of GChem 2 that is pretty much physical chemistry. All right? The only type of physical chemistry I like is when I lift up chemicals, right, to keep in shape. That's my physical chemistry. But this is actually pretty cool. I like kinetics. I did take kinetic courses in grad school that really pushed me to the limit, honestly. So here we go. So notice that you have a little hump or bump. That little bump represents your transition state. So you need a little bit of energy to go from R all the way to the transition state. If you don't have enough energy, what's going to happen? The reaction is not going to go, so it's going to come back. And so you're not going to have a reaction. Now, if your transition state is low, you can easily jump it with a little bit of heat by heating the reaction a little bit, and that makes the reaction go to completion. Because the transition state is too low, we think this reaction is fast. So it's almost like if you have a little obstacle to jump, you can jump it. But if you have enough energy going on the other direction, the reaction can become unstable. You can go back to the beginning. And so that's why it's unstable. All right? Notice also that the delta G is negative. So because the products are lower in energy than the reactants. So when you subtract products minus reactants, you get a delta G that is negative. All right? So here's the definition of delta G. Delta G is equals to the enthalpy of the reaction minus the temperature multiplied by the entropy. All right? So the enthalpy is defined in a few words, is defined as the amount of heat that the system has. All right? So when you have a reaction vessel, when you are mixing something in a vessel, that is a universe. It's a universe of itself. That reaction wants to create something, wants to do something. All right? Just like right here where we are, UTC is a universe. They call this a university, right? Because it's a universe. You have the famous people here. You have famous athletes. You have famous professors. Not so famous people. Not so famous athletes. Not so famous professors. But it's our universe. You know where the cafeteria is. You know where the bookstore is. So that is a universe. And so every universe has heat, and every universe has chaos. The entire universe is filled with chaos. That's what entropy measures. Entropy measures the amount of chaos or disorder in the universe. All right? So your delta G is going to be then equals to enthalpy minus the temperature times the entropy. Now, take a look at the T. That's very important because that's what chemists figure out. They say, okay, if I cool this reaction down to 0 or to minus 0, I can get rid of the disorder inside of the flask when I'm running this reaction. All right? So, what's happening with the molecules? The molecules are like crazy. Imagine you have a can of hairspray, in your bathroom, and you don't use that can that day, then you go to sleep. You wake up the next morning, still don't use it. You use the can of spray on the third day. During those 3 days, inside of that can, those molecules have been collided to each other. There have been some elastic collisions where, just like when you're playing pool, you hit one molecule and the one flies away, or both fly in different directions. But there's also head-on collisions where the force is perfect in both of them, and decomposition happens. Both of those molecules, they collide perfectly at the right time, and then they get destroyed. So eventually, if you don't use your hairspray after 1 year or so, you'll see that when you try to put it on, it's only air that shoots out because your chemicals have died. And that is because of the amount of entropy that the flask, that the can has. All right? So scientists have figured out that if you cool down the reactions, you're going to break and slow down those molecules until they're going like this. So then they're going to do like this, right? So they're going to slow down. And so, this is the principle how you can control a reaction. And we're going to learn that in detail when we do enolates. Enolates are like the best example. And the greatest thing that happens for pharmaceuticals, because we can then choose where do we want to put that bond. If we want to put it up, that wedge, or down dash. It's great. It's awesome. So for now, let's analyze the reactions that we have here. So when we have a delta G that is negative, then we call this exergonic, meaning the reaction is liberating heat. This reaction is fast because it has a low hump to jump, and it's unstable because the transition stays so low, it can go back and be reversible. Now, B is a different reaction. Notice that B still has a delta G that is negative, but you have a high activation energy. And that high activation energy is going to make this reaction unreversible. This reaction will only go to the products. Yes, ma'am?
Is exergonic the same thing as exothermic?
Exactly right. Very good. So exergonic and exothermic relate to the same thing. They are interchangeable, and they both denote that heat is being released into the surroundings. So when you're running and you get really, really hot, your body wants to cool you off. So that's why we have sweat. And if you're running in the cold, you can see that heat escaping from your head. It's kind of you can see the smoke. That is an exergonic reaction. All right. So C, on the other hand, notice that C, on the other hand, has a small hump, but the delta G is plus. Means the energy where the products are formed is higher on the table here on the chart than the reactants. So when you subtract products minus reactants, you get a delta G that is plus. So this reaction is opposite, is cold. It will absorb heat. And you're going to tell me, well, heat and cold, isn't that related? Yes, it is related. Both are variables of temperature, right? Just like Albert Einstein said, cold is the absence of heat, and darkness is the absence of light. And he also went on to say that evil is the absence of God. That's how he could prove that there was a God. That's why I like Albert Einstein. So he was kind of cool about that. This is what cold means. Cold means the absence of heat. And the reaction turns cold because it's absorbing heat. It's absorbing. It's doing the opposite. If you take ammonium chloride and you dissolve that in water and you mix it, you're going to feel that the vessel is going to get really, really cold. So the reaction is absorbing heat from the atmosphere, from the surroundings. So it's going to grab air or water from the air, and it's going to get so cold that the water around it is going to turn into ice, and it's going to make it feel even colder. Notice that this activation energy for D is also high. So here you have a slow, stable endergonic reaction or endothermic. Notice that it's stable. D and B are stable. Imagine you are rock climbing a wall. You're going to take a while to get to the top. So you are slow to get there, but you're stable. So slow and steady is equal to being stable. All right? So that's what this is it. So the transition state is defined as delta G double dagger. And so because one is like two T's combined, so TT or double dagger, the first T refers to transition, and the second T comes from state. State has a couple of T's there. So they figure they use two T's to define this. So that's what the definition for that is. Let's see, what else can I say about this slide? All right, so we're going to learn that this is it. I mean, life is not that complicated. Life is simple, actually. We have these four types of reactions that happens at any time. So these are the four cases. All right, let's see what else I have. I'm going to skip this for a second. I'm going to go here. So notice that this is another reaction coordinate here. We see that we have two humps. The number of humps or bumps, depending on how the book defines it, is your number of reaction steps. The higher the transition state, the highest transition state that you see is what is called the rate limiting step or your rate determining step. So it's going to be defined as those: rate determining or rate limiting step. So it will be the one on the highest. So in this case, it will be transition state 1. The intermediate that we have here in the middle is actually a product of the first step. You notice that? You went from reactants to intermediate, and then that's the first step, and then you go from intermediate to products. That will be your second step, and that is denoted by the two bumps. Notice that the transition state 1 will resemble the products because the activation energy is closer to the value where the products are. And likewise, transition state 2 also resembles, now in this case, resembles the product, which is the intermediate shown here, because it's too far away from the products. All right? Then I talked about some of these things. We have in detail problems similar to this slide. I'm not going to go over this slide because we're going to be practicing. But here we're going to find out that at first glance, this reaction has 3 steps. The rate determining step is the reaction going from A to B because the bump is the highest. Yeah, well, I might as well just finish here. We're also going to know that endergonic reactions are A to B and B to C. You see that? And you also see that it says, is the second form intermediate C more apt to revert to reactants B or to form products? The answer is to form products because the activation energy of going from C to D is smaller. You notice that we can cut this through over here. This activation energy from C to D right here is smaller than going from C back to B. All right? And so that's what this is trying to say here. All right, so let's go on and start our practice homework. I think that was a pretty good introduction of what we need. All right. Number 1 says calculate the degree of saturation in the following formulas, and then draw as many structures as you can for each. This is a really good exercise. So let's start here. So we have C4H8. So 2 times N. Let me get a different color pen. 2 times 4 is equal to 2 times N plus 2. I don't have a nitrogen. Minus the number of X, which is 8, divided by 2. So what do we have here? 2 times 8 is 4. 4 plus 2. I'm sorry, 2 times 8. 2 times 4 is 8. Plus 2 is 8. Sorry. Can't talk. Sorry. The dyslexia is killing me. Let me reset. 2 times 4 is 8, plus 2 is 10, minus 8, that's 2. 2 divided by 2 is 1. All right, that sounded better. All right. So we have 1 du. All right, so let's try to build some molecules with this. So one example that I would say, okay, I need to have 4 carbons and 1 du, so I'll put a double bond there. All right. Notice that I have 3, 6 hydrogens, 7, 8 with the double bond here. The hydrogens on the double bond. There's no hydrogen right here, guys. There's no hydrogen right there because that is an sp2 carbon. All right. So I'm gonna delete this, and also gonna delete this because I want you to get used to linear structures. All right, likewise, you could have done this to go say, okay, I have 4 carbons in a row and 1 double bond. That's cool. You got that one, Ben, right? All right, I knew it. All right, you can move the double bond around and say, like this. I like to make it really nice. All right, so that's another one. How about this? A cyclobutane. That is 1 degree of saturation. Notice that I have 2 hydrogens on each of these carbons, so that's a total of 8 hydrogens. One more. How about I make a cyclopropane and a methyl group? That would be 5. Yes, sir. You have another one?
Did you also do cis?
Oh my goodness. See, you're the powerhouse, man. Awesome. You are the man. What Ben is saying is there's another possibility. Cis. My goodness. I didn't even think about that. Good job, man. Awesome. So, yes, this will be trans and cis. All right. Very good. Let's do the next one. The next one has some really interesting, I came up with some interesting molecules you'll see. C4H6. So, it's 2 times 4 plus 2, because I don't have a nitrogen, minus 6. My number of X is 6 hydrogens. Divide that by 2. I get 2 times 4 is 8 plus 2, 10. 10 minus 6 is 4. 4 divided by 2 is 2. All right, so I need 2 degrees of saturation. How about I start with this? A 4-member ring. Well, I have a lot of them here, so I'm gonna make myself some room here. 4-member ring, butane, cyclobutane plus a double bond, so cyclobutene. That will fit. So I had 2 degrees of saturation. Notice that I have 1, 2 hydrogens, 3, 4, 5, 6. So I have total 6 hydrogens. Oh, I didn't mean to erase everything. All right. Next, I'm gonna shrink this molecule to a cyclopropene with a methyl group. All right, that's getting a lot of strain there. You notice that? Imagine having a double bond on a cyclopropane. Get ready for the next strain. Look at this one. This is, what if you have 2 cyclopropanes rings at fuse? Whew. That would make for some really good explosive, I think. All right. Then we have this guy, a diene. It could be like that. And now Ben gave me an idea, right? Notice this. This is called the, you know what they call this? They call the S-trans. We're going to learn that later. That is the S-trans because that sigma bond here is denoted as an S. Also, if you rotate that double bond down, you have this, the S-cis. Right? Where S means sigma. All right. So likewise, I'll have also, I could have a cyclopropane with a double bond here. I could also have this. How about that? That's 3 degrees of saturation. Triple bond with 2 methyl groups attached on the sides. Its carbon has 3 hydrogens, so it's total 6. I have 4 carbons and 6 hydrogens. How about this then? Triple bond with an ethyl group, or this one. What if I put the double bond here next to where the methyl group is? So that would be everything that I got. Ben, do you think of something else? All right, that sounds good. How about you, Jeff? You thought of something else? I think this might be it. All right. Let's do the next example. C3H4. All right, I had them in. So we're gonna cover this page. That's what I covered in the morning. 2 times 3 plus 2 minus 4. Divide all that by 2. I get 2 times 3 is 6 plus 2 is 8. 8 minus 4 is 4. 4 divided by 2 is equal to 2. All right, so here I will do this one. How about I have this? Haha, check this out. You know how they call these alkenes, these dienes? They call them cumene. So this would be a cumene because the double bonds are accumulated. So they're accumulating next to each other. How about this one? I have 1 degree of saturation here and a double bond there. That's 2 degrees. And finally, I could only come up with 3. A triple bond, that's 2 degrees of unsat plus a CH3. All right. Let's do practice on the other things here. So what I want you to see here is in this exercise is how these degrees of saturation are affected by the different groups that we just mentioned, the oxygens, the nitrogens, and the halogens. All right, so here we go. The first one has a nitrogen. So that's the first one we're going to be using that has a nitrogen. So that's 2 times 6 plus 3, right? Because we have a nitrogen now. The moment that you have a nitrogen, you have to add 3. Minus the number of X, and that is 5. Divide all of that by 2. So 2 times 6 is 12 plus 3 is 15. 15 minus 5 is 10. 10 divided by 2 is equal to 5. All right. I'm not going to do any examples here of structures. Let's just calculate this. So now let's take a look at the effect of oxygen on it. Without the O2, notice that the du, let's see what happened to the U. So I'm not going to say anything. So 2 times 6 plus 3, because we have a nitrogen in there, minus 5. Notice that divided by 2, I have this exact same thing as before. All right, so oxygen didn't do any effect. Now we have the next example. We have 2 times 8 plus how many? Plus 2, right? Because we don't have a nitrogen. Minus how many? 12. Excellent. So now we have 12 as the number of X's because we had to add the hydrogens with the halogens. Divide all of that by 2. And what do we get here? 2 times 8, 16 plus 2, 18. 18 minus 12 is 6. 6 divided by 2 is equal to 3. All right? All right, let's do the next one. 2 times 9 plus 2, right? Because I don't have a nitrogen. Minus how much? 18. So I have 16 hydrogens and 2 bromines. That's a total of 18 by adding the hydrogens with the halogens. Divide all that by 2, and then we get 2 times 9 is 18 plus 2, that's 20. 20 minus 18 is 2. 2 divided by 2 is 1. All right. Lastly, we have here that we have 2 times 10, that's equals to 20, plus how much? 4. Very good. So if we had 1 nitrogen, it would have been plus 3, but because we have 2, we add 4. We keep on adding an extra 1 because of the nitrogens. If we would have had 3 nitrogens, then it would have been plus 5, and like that. All right. Plus 4 minus how many? Minus 12. Divide all that by 2. Let's see what we got here. So 2 times 10 is 20. 20 plus 4 is 24. 24 minus 12 is 12. And 12 divided by 2 is equals to 6. All right. Very good. So let me write something down here as a note. Okay, so I'm going to say there are 2 nitrogens. Thus, the formula 2n plus 3 adds 1 more to become 2n plus 4. All right. I could keep going, but since the morning I just stopped there, I'm going to stop here now, so we can dismiss a little earlier today. All right. Have a wonderful day, guys. I'm going to stop the recording.